today's lesson is short, it's profound, and we're going to be talking about entropy. And when we talk about entropy, we're going to be talking about it in two different ways that seem really different but are actually related. And my job is going to be to try to put those two things together. When we talk about entropy, the first way in which we can define entropy is in terms of how much entropy is added or subtracted from a system when a process happens. So going to our PV diagram right here, we're going to have a process that's going to take us from point A to point B. And so the amount of entropy change that occurs during that process is going to be the amount of heat that flows into or out of that system divided by the temperature, the Kelvin temperature of the system. Let's actually see how this process and this concept of entropy would work out in a practical situation. Imagine that I take some hot water at, let's say, 50 degrees Celsius. And I take some cold water at, let's say, 25 degrees Celsius. And I put it in contact with each other. Now here I've represented the hot and cold as being isolated. In real life, what's going to happen to the two of them? They're going to mix. That's exactly right. But because entropy is what we call a state variable, then even as they mix, the hot water molecules and the cold water molecules can still be identified. They're going to lose heat, and as a result of that, they're going to hit the same temperature. And if it's equal amounts of hot and cold, you can even figure that final temperature, which is going to be 37.5. So this is the old Simpsons thing, right? The Simpsons Halloween episode. Bart comes into the cottage and he tastes the Papa Bear's porridge and it's too hot. And he tastes Mama Bear's porridge and it's too cold. And he says, "This doesn't take a brain surgeon," and he pours the two together. And it's just right. So this is lukewarm now at 37.5. Well, to get there, what had to happen was heat had to flow out of the hot and had to go into the cold. And I'm just going to make up a number. Let's say that we had 500 joules of heat go from the hot to the cold. Now here's the weird part about it. The system overall did not suck in any heat from the outside. We're stipulating that it is perfectly insulated. But even though no heat comes in from the outside, there is still heat exchange between the hot portion of the system and the cold portion of the system, specifically 500 joules worth of heat. So we can calculate the entropy change for the hot water, and we can calculate the entropy change for the cold water. Actually, we can only estimate it because technically the hot is becoming colder as it goes, right? And the cold is becoming hotter. So we would have to do some fancy calculus to do it just right. But we can estimate that the entropy change for the hot water is going to be equal to the amount of heat that flows out of divided by the temperature. That's going to be negative 500 joules because the hot is losing the heat here, divided by its Kelvin temperature, which is going to be 323. And go ahead and compute that number. And we'll set up the same entropy change for the cold. And this guy is going to be 298. What do you have for the first one? And we're going to measure entropy entropy in terms of joules per Kelvin. And then what about for the bottom one? Anybody have that number? And that's positive. And what does this mean for us practically? Well, here's what it means. Even though the system did not take in any heat from the outside, nevertheless, its overall entropy, the delta S for the system, the hot plus the cold, was non-zero. In fact, it was a positive number, 0.11 joules per Kelvin. Now, I'm presenting entropy only in terms of heat at this time, heat per temperature, but I want you to observe something, that the positive entropy result that we got right here was not an accident. Mathematically, it had to happen that this quantity here would be a positive value. Why is that? Because the heat that flowed from the hot reservoir was at a hotter temperature. And therefore, that meant that the number that we got here had to be smaller in magnitude than the change in entropy that we got for the positive, the thing that was sucking in heat, because heat always flows from hot to cold. So when we observed that delta S for the system was positive, that was a simple mathematical consequence of the fact that heat always goes from hot to cold. And so what we conclude, and this is what Clausius concluded, who invented this concept of entropy in the 1860s, he concluded that for an isolated system, delta S must always be positive, because heat always flows from hot to cold. The negative entropy that the hot part of the system is going to achieve by having its particles slow down will always be less in magnitude than the positive entropy that the cold part of the system receives by having its particles speed up. In fact, this is another way of saying that you can't achieve absolute zero in temperature, because if you did, any heat that would go into that system would increase the entropy by an infinite amount. All right? So there's that. I'd like to see the same point on a PV diagram. So let's imagine we've got some process. It's going to take us like here. In fact, let's make that process be a Carnot engine process. So we're going to go along. Remember how it goes? An isotherm. And we're going to go adiabatically, and we're going to go back along an isotherm, and then up adiabatically again. So the process goes like that. So here's our Carnot engine. So, what can we say about this? Well, along the isotherms, the temperature is going to remain constant. It has to. The reason it has to remain constant is that we are moving along a point where the internal energy remains the same. The product PD remains the same, and therefore the temperature remains the same, because PV equals NRT. So that means all along here, I can compute the entropy for this process by observing that because delta U is equal to 0, all of the work that is spit out during that process is equal to the amount of heat absorbed by that system, right? So I can immediately compute Q over T for the hot part of the system. Let's call this a B right here. And the temperature here is going to be the hot temperature, the upper isotherm. Okay? So we're going to absorb heat into that system. We're going to turn it into useful work. And here it is. Now we do the whole adiabatic portion of that. Remember that adiabatic means that no heat is sucked in because it happens really quickly. So because it happens really quickly, no heat is sucked in, and Q is 0. So we have no change in entropy for that part of the system. Now we spit some of that exhaust heat out, but we're doing it now at a lower temperature, right? And so as a result, when we spit some of that exhaust heat out, our efficiency is never 100%, and so we're going to spit out less heat and so on and so forth. The negative amount of entropy that we have for this process is always going to be less than the positive amount of entropy that we have for that process. And we go back adiabatically again, and no entropy change there. And so we have delta S for the hot part of the process is always going to be less in magnitude, greater in magnitude than the delta S for the cold part of the process. And as a result, that means that delta S for one entire cycle is going to be greater than 0. What's the conclusion? That some energy will always be wasted, essentially. And what we're going to do is we're going to end up increasing the entropy of the surroundings. Now, what does that mean? What does this entropy mean in terms of molecular motion? I'd like to take a molecular point of view here and consider what entropy has to do with molecular stuff. A second approach to thermodynamics developed, other than heat, and that was to consider the idea of possible states of the system. So let's take a minute to consider possible states. And this is going to seem unrelated to heat, but it's not. Possible states of the system are the ways that the molecules can be arranged and how fast and their velocities. So what we're really talking about are the sets of velocities for the entire system. And if you want to, imagine a mathematical, multi-dimensional construction, an array or vector, that has the positions and the velocities for each one of the particles. So that would be a huge, very, very large dimensional space. Then when we go from one position in velocity to another, we're changing states. Conceptually, that kind of makes some sense. Now here's the thing. Some states are special, and some states are not. And by analogy, let's consider, this is for a set of particles, but let's consider the states of a deck of cards. The states of the deck of cards are going to be the ways in which the cards are arranged. And the ways of arranging are also either special or not special. For example, a special state would be to have all the cards arranged ace through king, spades, hearts, diamonds, clubs. That would be a special state. A not so special state would be to have some essentially random arrangement, like 10 of diamonds followed by the ace of cards followed by the whatever. It's what you get when you shuffle. Right? Okay? So the shuffled states are essentially equivalent to each other. And the special states are relatively few in number. We're going to call the special ones the ordered states, so that they have some order to them. I mentioned ace through king as a possible ordering, but we could do something like having all 4 aces, followed by all 4 twos, followed by all 4 threes, etc., up through all 4 kings. So any specially ordered state is going to be specially ordered. All the others are going to be disordered, essentially. Now here's the question. Which one are more common? The shuffled states, right. That's exactly right. Likewise, for the particles, any special state where the particles all show some kind of order. For example, maybe they're all frozen in space in a nice little regular lattice. We would call that a crystal. Okay? Or maybe all the particles are in one corner of the room and everywhere else is empty. Those would be special or ordered states. And the states where they're just bouncing around randomly, coming into contact with each other, those are all the disordered states like that. Which one are more common? Definitely the random disordered states. Okay? And we could do graphs and bell curves and blah, 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 but I think you get the picture. Now here's the deal. When we introduce heat into the system of particles, we are introducing motion. We are increasing the rate at which the particles transition from state to state to state to state. When we shuffle the cards, we are introducing motion into that deck of cards. We are causing our cards literally to transition from one state to the other. And the faster we shuffle, the faster our state transitions happen. You see it? Now here's the thing. Just speaking in terms of probability, when I transition from one state to the next, am I more likely to transition into an ordered state or a disordered state? So if I increase the rate at which I transition states, I am going to increase the likelihood that I transition to a disordered state. That's it. The more heat I pump into a system, the more I am going to increase the likelihood that that system goes disordered. The more motion I introduce into a deck of cards, the more likelihood there is that I'm going to transition to a disordered state. So if I take a deck of cards in my hand, and I play the 2-year-old's favorite game, 52-card pickup, throw that deck up in the air, there is a high, overwhelming likelihood that that deck of cards is going to come down in a disordered state. The only way that could not happen, basically, would be one of two ways. Either the deck fails to come apart because the cards are glued together or something stuck together, right? That would correspond to chemical bonds sucking these particles into orderly arrangements. Or that by some miracle of statistics, these cards all go up in the air and they come down into a nice orderly lattice, ace through king, ace through king, ace through king, ace through king. Not going to happen, right? Could happen, but it's not going to happen. And because of that, what we say is that when heat transitions through a system, when heat is exchanged, that always increases entropy. Why? Because I am essentially causing these particles to transition through their states, and when they do, they head towards the most likely state, which is the disordered states. So that's really the concept of entropy. Lots of profound implications for this. But among other things, it means the following. If you want to decrease the disorder, you have to put in useful work. This is mom wisdom. That room ain't gonna clean itself. That's a statement of second law of thermodynamics. The delta S for a system is always positive because disordered states are more likely. Same thing is true about like environmental cleanup, right? So we can do environmental cleanup, but that process of environmental cleanup is going to require doing work, and the work is going to have to come from some source, and that source is going to increase the entropy in our system. So we can do it, but at the cost, we can clean up, say, trash in the creek, but at the cost of thermal pollution. How is it manifested in human beings? Well, basically, we eat, And we eat, we have waste products, and those waste products reflect taking molecules that are in highly ordered states like broccoli and turning them into more disordered states like food. Or more disordered states like breathing out carbon dioxide gas, right? Carbon dioxide gas is clearly a much more disorderly arrangement of the molecules of carbon than the original carbon atoms that were in broccoli. So all heat processes tend towards entropy. Now here's a really good question. Given that that's the case, why is it that there's any order on Earth? Well, the Earth is not an isolated system. It's receiving a heck of a lot of energy from where? From the sun. That's exactly right. And so the sun's action on the Earth, warming, cooling, and so on and so forth, provides opportunities for disorder, yes, but also opportunities for chemical bonding to happen. And chemical bonding essentially forces of attraction fighting against that. I'll see you later.